Every time a rocket launches from Kennedy Space Center, every time a Mars lander deploys its parachute at supersonic speed in the thin Martian atmosphere, every time NASA engineers redesign a wing or predict how exhaust plumes will interact with a launch pad, there is software running behind the scenes that almost nobody outside the aerospace industry has ever heard of. It is called LAVA. It stands for Launch, Ascent, and Vehicle Aerodynamics. It was developed over 15 years at NASA's Ames Research Center in Silicon Valley, refined through some of the most demanding computational challenges in the history of spaceflight, and used internally by NASA engineers to solve airflow problems that no other software in the world could handle as quickly or as accurately. For over a decade, it was NASA's tool and NASA's tool alone. As of April 2026, that changed. NASA has officially released LAVA to the United States aerospace community, making one of the most powerful computational fluid dynamics software packages ever built freely available to university researchers, private companies, startups, and individual engineers across the country. And the implications of that decision for everything from supersonic airliners to delivery drones to the next generation of Mars missions are just beginning to be understood. To understand what LAVA actually does and why it matters so much, you need to understand the problem it was built to solve. In aerospace engineering, one of the most fundamental challenges is predicting how air moves around a vehicle. Whether that vehicle is a rocket climbing through the atmosphere at thousands of miles per hour, a spacecraft decelerating from orbital velocity during re-entry, or an aircraft wing generating lift at cruise altitude. The physics governing these situations is described by a branch of mathematics called computational fluid dynamics, or CFD. CFD involves solving sets of differential equations that describe how fluid, in aerospace, that fluid is air, moves, accelerates, turns, compresses, and interacts with surfaces under varying conditions of temperature, pressure, and speed. These equations are not simple. For any vehicle geometry more complex than a smooth sphere, the number of calculations required to solve them accurately is enormous. Before modern supercomputers, the only way to understand airflow around a new design was to build a physical model and put it in a wind tunnel. Wind tunnel testing is accurate, but it is also expensive, time-consuming, and physically limited. You cannot build a wind tunnel that accurately replicates the supersonic conditions of the upper Martian atmosphere, for example, or the acoustic environment of a rocket launch pad as a 9 million pound vehicle ignites its engines and begins to climb. CFD software provides an alternative. Instead of building the physical model and testing it, engineers build a mathematical model of the vehicle, define the computational domain around it, set the initial and boundary conditions, and let the software solve the flow equations numerically across millions or billions of discrete points in space. The result is a detailed picture of how air will behave around that vehicle under those conditions. Pressure distributions, temperature fields, shockwave locations, turbulent eddies, acoustic signatures, all of it computed in software before a single physical component is manufactured or tested. Good CFD software saves enormous amounts of money and time. It catches problems before they are built into hardware. It allows engineers to test hundreds of design, variations in the time it would take to run a handful of wind tunnel experiments, and it enables the simulation of conditions that simply cannot be replicated on Earth, like the supersonic Martian atmosphere or the acoustic environment of a rocket launch at full scale. The problem that led NASA to develop LAVA in the first place was exactly this kind of simulation gap. Most CFD software on the market forces engineers to make a choice. They pick one type of computational grid, one type of solver, one set of numerical methods, and they accept the limitations that come with that choice. Different types of flow problems are best handled by different types of computational approaches. High-speed, shock-dominated flows are handled well by structured Cartesian grids with immersed boundary methods. Flows around complex curved surfaces with fine geometric details are better handled by unstructured polyhedral grids that can conform to arbitrary shapes. Flows that need to capture turbulence at multiple length scales require yet another approach called scale-resolving simulation, which is far more computationally demanding than simpler turbulence models, but far more accurate for problems where turbulent mixing, acoustic noise, or flow separation is critical. Before LAVA, engineers had to choose one of these approaches and live with the trade-offs. LAVA was built from the ground up to be grid flexible, meaning it can handle all three types of computational grids, couple them together seamlessly through an overset interface, and apply the right numerical methods to the right parts of the flow domain simultaneously. NASA's LAVA team lead, Jared Duensing, described what this means in practice by saying that where most CFD software hands engineers a hammer, LAVA hands them an entire toolbox. The development of LAVA began more than 15 years ago, rooted in a very specific engineering crisis at Kennedy Space Center. NASA was redesigning the launch infrastructure at KSC, the flame trenches, the flame deflectors, the water suppression systems, the mobile launcher towers, and engineers needed to understand with high precision how the enormous pressure waves, thermal loads, and acoustic energy generated by a rocket ignition would interact with all of those structures simultaneously. This was not a problem that existing CFD tools handled well. The geometry was too complex, the physics was too multi-layered, involving simultaneously high-speed gas dynamics, multi-phase liquid gas flow from the water suppression systems, heat transfer through solid structures, and acoustic wave propagation for any single existing solver to capture accurately in a reasonable amount of time. The LAVA team at NASA Ames, led by Aerospace engineer Seton Kiris, began building a framework that could. They designed it from the start to handle multiple grid types, multiple physics modules, and massive parallelization across thousands of computing cores simultaneously. In over 15 years of continuous development, they refined and expanded it through one NASA mission after another. The list of missions LAVA has contributed to directly reads like a catalog of the most demanding aerospace engineering problems of the past decade and a half. When NASA was preparing the Artemis Y launch, the first flight of the space launch system, the most powerful rocket NASA has built since the Saturn V, engineers used LAVA to simulate the complete launch environment at Kennedy Space Center's Launch Complex 39B. The simulations computed how the SLS's exhaust plumes interacted with the flame trench, the water suppression system, the mobile launcher, and the surrounding infrastructure, modeling pressure, temperature, and acoustic loads across the entire launch pad. Geometry and detail that no wind tunnel test could replicate at that scale. For the Artemis II mission, LAVA was used to simulate the aerodynamics of a design modification to the SLS core stage, a pair of 6-foot-long strakes added to smooth out vibrations induced by airflow during ascent. Without the simulation, validating that design change would have required additional wind tunnel tests and physical testing, each costing significant time and money. On the Mars side, LAVA has been central to solving one of the hardest problems in planetary entry: supersonic parachute deployment. When a spacecraft enters the Martian atmosphere, it is traveling at hypersonic speed and must decelerate to subsonic speed in an atmosphere that is only about 1% as dense as Earth's. Part of that deceleration is accomplished by deploying a large parachute at supersonic speed, a sequence of events where the parachute inflates in a chaotic, violently unsteady flow environment at conditions that are physically impossible to replicate in any wind tunnel on Earth. NASA's Perseverance rover, which landed on Mars in February 2021, used a parachute whose design was selected in part based on LAVA simulations of parachute inflation under supersonic conditions. The LAVA team used their software, running on NASA's Pleiades and Aitken supercomputers, to simulate the fluid structure interaction of the parachute inflating, the way the fabric deforms, the way the shock wave from the spacecraft interacts with the wake behind it, the way the supersonic flow threads through the openings in the canopy. These simulations helped NASA's Jet Propulsion Laboratory select the final parachute design for Perseverance and provided validation data for future Mars missions. LAVA is now being extended to support upcoming missions to Titan and Venus, where the same problem of atmospheric entry and parachute deployment arises in entirely different atmospheric conditions. LAVA was also deeply involved in one of NASA's most ambitious aeronautics programs in recent years, the X-59 quiet supersonic aircraft built by Lockheed Martin for NASA's QUESTI mission. The X-59 is a full-scale supersonic demonstrator designed to fly over populated areas and produce a sonic thump rather than the traditional sonic boom, reducing the perceived ground-level noise to a level that might eventually allow commercial supersonic flight over land, something that has been banned in the United States since the Concorde era. Designing the X-59 to produce a specific, controlled sonic signature required thousands of high-fidelity CFD simulations of the aircraft's supersonic performance at a wide range of flight conditions and control surface configurations. LAVA ran most of those simulations at NASA Ames, and in one case, the detailed aerodynamic analysis caught a significant flaw in the design of the aircraft's nose, a flaw that, had it not been identified in simulation before the aircraft was built, could have threatened the mission. The LAVA team's space marching technique, a numerical method they developed specifically for supersonic boom prediction, cut the computational cost of each simulation roughly in half, making it possible to build the massive database of simulations required for pilot training and flight planning tools that the program depended on. What has now changed with the public release of LAVA is that all of this capability, developed through 15 years of mission-critical work on NASA's most demanding aerospace problems, is available to anyone in the United States aerospace community. University researchers who previously had to work with older, less capable CFD codes can now run the same type of scale-resolving simulations that NASA engineers use to design Mars parachutes and analyze rocket launch environments. Small companies developing electric air taxis, delivery drones, advanced rotorcraft, or novel aircraft configurations can now optimize their designs with the same precision that previously required either NASA, collaboration, or access to enormously expensive commercial CFD software licenses. Startups working on next-generation launch vehicles can simulate their aerodynamic environments with a tool that has been validated against some of the most complex real-world aerospace data ever collected. The access barrier that previously put this level of simulation capability out of reach for most of the commercial aerospace industry has been removed. Lava runs on modern GPU-based computing hardware, the same type of specialized processors that power artificial intelligence training, video rendering, and scientific computing in data centers around the world. This is a critical advantage because GPU computing has become dramatically cheaper and more accessible over the past several years. Where traditional CFD software was optimized for clusters of general-purpose CPU processors, the kind of hardware that only large organizations could afford to operate at scale, Lava's compatibility with GPUs means that a well-equipped university lab or a medium-sized aerospace company can run simulations on hardware that is commercially available and relatively affordable. On NASA's flagship GPU-based supercomputer, called Cabeus, Lava has demonstrated exceptional efficiency on the most demanding simulation workloads in NASA's computing portfolio. That same efficiency translates to better results per dollar of computing time for anyone in the commercial sector running the software on their own GPU hardware. Duenzing, the Lava team lead at NASA Ames, described the intent of the release explicitly. He said, "This is not only about releasing software, it is about accelerating innovation. When university researchers can run more complex simulations, and when small companies can optimize designs with NASA-grade precision, the team is not only sharing tools, but unleashing potential." That framing is significant because it reflects a broader shift in how NASA thinks about its role in the aerospace ecosystem. For most of its history, NASA developed tools and kept them internal. The knowledge stayed within the agency, applied to agency missions. The Lava release is part of a different philosophy, that the highest return on the public investment that built Lava comes not just from using it on NASA missions, but from releasing it into the hands of the entire U.S. aerospace industry and letting thousands of engineers, researchers, and innovators apply it to problems NASA's own teams would never have the time or resources to address. The timing of the release connects directly to several of the most significant challenges in commercial aerospace right now. The advanced air mobility industry, urban air taxis, autonomous delivery drones, electric vertical takeoff and landing aircraft, is expanding rapidly, and every company in that space faces the same fundamental engineering challenge: designing vehicles that are aerodynamically efficient, acoustically quiet, and safe across a wide envelope of operating conditions. Lava's capability for simulating rotor aerodynamics, acoustic noise propagation, and turbulent wake interactions is directly applicable to these problems. The commercial supersonic aviation sector, where companies like Boom Supersonic are developing next-generation supersonic airliners, faces exactly the kind of sonic boom and aerodynamic performance simulation challenges that Lava was developed to handle on the X-59. And the commercial launch industry, where dozens of companies are developing new rockets and upper stages, faces the same launch environment simulation problems that drove Lava's original creation at Kennedy Space Center. What NASA has done by releasing Lava is not a small thing. It is the transfer of 15 years of accumulated engineering knowledge, embedded in working software, validated against real mission data, from a government research agency to the entire commercial aerospace ecosystem of the United States. The problems that Lava will be applied to in the next decade, by researchers and engineers who have never worked at NASA and are solving problems NASA has never considered, are impossible to predict. But the history of technology transfers like this one suggests that the applications that emerge from the broader community will eventually surprise even the people who built the tool. Lava went into the world this week as a solution to the hardest fluid dynamics problems in spaceflight. And what it becomes in the hands of the aerospace industry is a story that has only just begun.